Hello everybody, my name is Juan Antonio Martinez from Odin Solutions, and in this video I'm going to introduce a general overview of the IoTCrawler architecture. This project was conceived with the objective of providing the next generation of internet search engines focused on IoT information. This way, IoT devices or their information can be crawled, discovered, and searched with the added value of doing this in a secure and controlled manner. With these requirements in mind, let's dive into the design and implemented architecture of IoTCrawler. Following a bottom-up approach, we can count with the following layers: micro layer, domain layer, interdomain layer, internal processing layer, and exposure layer. Finally, since IoTCrawler has covered the topic of security and privacy from a traversal point of view, we have in this architecture the security, privacy, and trust pillar. In the micro layer, we define the mechanisms to integrate the IoT information into the IoTCrawler architecture. It comprises the crawling and semantic annotation processes. The domain and interdomain layers comprise the core of our architecture, based on what we have called metadata repositories, which we are referring as MGR. These are the brokers responsible for distributing the semantically annotated information to other components of the architecture. Actually, the federated MGR is the endpoint and the reference for the upper layer's components. The internal processing layer purpose is to process the information registered from the micro layer to extend it, adding metadata, and to provide an agile way to search over this information by creating indices and also a ranking operation. The monitoring module is responsible for watching the queries processed and the results to find if there are faults and even if it is required to create virtual information in absence of real one. The exposure layer is the endpoint of our IoTCrawler architecture, comprising both an orchestrator and a search enabler module for handling the different queries performed by users and services. Finally, security has been proved to be a cornerstone aspect that must be addressed in the IoT domain from the beginning. For this reason, we have defined a traversal pillar responsible for providing authentication, authorization, and privacy in the IoTCrawler architecture. This way, ranging from the registration phase from the provider's point of view to the access to the information from the consumer point of view, and also from an internal perspective, all the interactions are performed in a secure manner. Now, let's focus on the different layers and the activities they are responsible of. The Southbound API for the IoTCrawler architecture is composed of the crawling and semantic annotation components. This API is the one that must be used by data providers in order to integrate new information into this framework. With the objective of allowing a high number of IoT platforms, this architecture is based on standards and open interfaces. More specifically, IoTCrawler is based on NGSILD, which stands for Next Generation Service Interfaces for Linked Data. This representation model and API is being standardized by the ETSI through the Industrial Specification Group for Cross-Cutting Context Information Management, also known as ISDSIM. Nevertheless, in the near future, IoTCrawler will be interoperable with other third-party platforms by the development of specific connectors. IoTCrawler has considered three different crawling strategies: IoT gateways, IoT brokers, and dynamic web crawlers. The first strategy covers the integration of IoT devices which can be located in a controlled environment, for instance, a smart home, which are discovered thanks to the use of an IoT gateway which scans the network and identifies the different smart appliances connected to the network. The second option represents other third-party IoT platforms and their corresponding distribution brokers, which include a relevant number of IoT devices and which can be integrated into the IoTCrawler framework defined by this architecture. So far, as previously commented, they must be compliant with the NGSILD standard. Otherwise, an adapter is required for integrating this information. Finally, dynamic web crawlers represent the ability of exploring hyperlinks and connections among web pages to crawl web data using standard web crawling techniques. The information integrated in our IoTCrawler framework must contain basic metadata so that further processing could be made over the registered information. Based on the NGSILD standard, IoTCrawler has defined a specific IoTCrawler model which is pushed into an MDR. This model is based on the IoT stream and which allows for specifying different sensor properties such as location, the sensor type, timestamps, events, or even quality of information. We have also included in this representation model security aspects such as data encryption or access control rules. The content management activity is performed by the core of our architecture, the MDRs. They expose an NGSILD interface. Our architecture considers the integration of different domains which have been represented in this diagram by domain 1 and domain 2. These domains can have a single instance of an MDR, or they can have a more complex scenario comprising a distribution of brokers. In our interdomain layer, we have defined a federated approach where the different representative brokers of each domain are integrated in what we have called a federation MDR. This is the endpoint for the upper layer components to query the information stored in the IoTCrawler framework. With the goal of representing IoT information, we have also defined a specific IoTCrawler ontology, which is the one that you can see. The central concept in this ontology is the IoT stream, which we can see in the center of the diagram in blue. This is linked to different entities such as source sensor, a geographical point, and also events related to the stream observation. Quality of information is also considered through the completeness, concordance, and timeliness properties. Finally, security is also addressed by introducing integrity properties such as the signature and also privacy by using encryption. Now it's the turn for processing the context information stored in our MDRs. This layer comprises 4 specific modules: monitoring, semantic enrichment, indexing, and ranking. The semantic enrichment component is connected to the Federation MDR following a publication subscription approach. This way, it is notified when new information is registered or updated. It performs an analysis of this information and extends the current metadata, adding quality of information properties which can be later exploited by the queries from the consumer point of view. The indexing component is responsible for making efficient search over the information stored in our Federation MDR. This module can index any property and use sharding for the purpose of being a scalable component. It also creates indices over spatial information by using a geohash approach, by which a region is associated to a specific tag to be easily accessed. Regarding the results that the user can obtain, we can identify 2 fundamental requirements. The first one is the provision of results in an efficient way. The other is that of selecting which way these results must be ordered. This is the role of the ranking component. This component sorts the results based on the relevance to the application. To do so, it can apply different ranking criteria, which can be as simple as by the proximity to the users, using the location information, or more complex options based on other quality of information attributes. Finally, the monitoring component, as its name indicates, monitors the queries performed over the IoT information. Once one of the offered results is selected or clicked. This way, it can detect if the resources are no longer available and act upon this, updating the quality of information of the resources. One of the value-added services that the monitoring component includes is that it can generate virtual information in absence of the real one. For this purpose, it applies machine learning techniques to extrapolate real values in the proximity of the requested region. The exposure layer is the one located at the top of our architecture and represents the Northbound API for external services. It comprises both an orchestrator and a search enabler component. The former is the one responsible for handling the different queries requested by user and services and communicating them with the indexing component to obtain a ranked list of results. The latter is the search enabler and is the one which provides an API for accessing the resources of the IoTCrawler architecture. It also provides a subscription mechanism based on RabbitMQ for notification on update over the information stored in the platform. With this slide, we finish this tutorial about the IoTCrawler architecture. We have covered all its layers, ranging from the micro layer to the exposure layer, describing their components as well as their functionality. We have also depicted both Southbound and Northbound API based on NGSILD for registration and querying. I hope you have enjoyed this tutorial and thank you very much for your attention.